The graph of y equals 2x cubed plus 3x squared minus 36x plus 9 is shown below. Why would 2 not be a good choice for x0, our starting value? We can see that there's a root close to -5, a root between 0 and 1, and a root between 3 and 4. OP wants to find the root between 0 and 1 and chooses to start at 1.9. What happens? Using a suitable starting value, find the root between 0 and 1 correct to 4 decimal places. So let's go back to part A. Why would 2 not be a good choice for x0? Well, 2 is at this turning point. So we'd end up with a horizontal tangent and we'll never find a root. So now what happens when we start at 1.9? Well, to start with, let's get our formula to use. We know the Newton-Raphson formula is xn plus 1 is xn minus f of xn over f dashed of xn. And here, f of x is 2x cubed plus 3x squared minus 36x plus 9. And so f dashed of x is 6x squared plus 6x minus 36. So xn plus 1 is xn minus 2xn cubed plus 3xn squared minus 36n plus 9 over 6xn squared plus 6xn minus 36. So we can set this up on the calculator, and I'm going to show you how to do that. So we know that OP is going to start at 1.9. So put 1.9 in and press press equals. And now 1.9 is the last answer. So what we can do is put in the formula, and we'll say answer, take away, use a fraction template, 2 times answer cubed plus 3 times answer squared, take away 36 times answer, add 9, divided by 6 times answer squared, plus 6 times answer, take away 36. And that's what I'm showing in this graphic over here. If I press equals, we get x1. If I press equals again, we get x2. And so using that technique, it's easy to build up a table. So 0, we know that we started at 1.9. We could see from my calculator that we ended up at -9.95. Our x2 is going to be -7.33, and so on. Each time we press equals, we get the next iteration. And what we can see from that is that we're going to find the root close to -5. The problem is that we started too close to a turning point, and so the tangent took us to a completely different part of the curve. So we're finding a root that's a long way from where we started. So what we're going to do is start closer to the root we want, e.g. start at 1. So this time we're starting at 1, but we're doing the same process. So x1 is going to be 0.083 recurring, and we continue to iterate. And what you're going to see is that to the accuracy of the calculator display, the number stops changing. So we can see that when we get to this point, there's no way that the fourth decimal place is going to change. We can see from iteration 4 the number is not changing to the accuracy of the calculator display. And that's what I was saying about how well this method works when it works. So we can say it's 0.2564, correct to 4 decimal places.